Welcome back to the 7th seminar of the Fik3505 Wireless Multiple Access Protocol course. In this seminar we will cover the power capture phenomenon in wireless channels. The reference material that we'll use in this seminar are 3 journal articles by Namislo, Godman and Saleh and Arnbach and Blitterswijk. Found on the website, journal articles 1, 2 and 11. To review where we are on the protocol classification map, we are in the on the left hand side in contention schemes, and we look at dynamic resolution and with probabilistic resolution of conflicts. So we are in the ALOHA protocol domain. So in this seminar we will review what happens in an ALOHA system in a cellular radio network setting. Here we have 2 terminals transmitting packets to a single base station. And due to the characteristics of the wireless communication channels, we know from the first seminar that packets can get lost due to channel errors, even though there is no collision at all. And what we'll add in this seminar is the phenomenon that packets received at different power levels may win a collision. This is called the capture. So the stronger signal may win over the weaker signal, and the signal to interference ratio may be high enough to allow for the correct reception of one of the packets, even though there was a collision. So let's look at this power capture phenomenon. We can see that a successful reception of a packet can occur for those terminals that satisfy the following condition. Here we write the received signal to interference plus noise ratio. We have the wanted signal power Pi divided by the sum of all the interfering powers plus the noise that will be received in a certain slot. And if this signal to interference ratio is larger than gamma naught, which we also call the capture ratio, then the packet I will be received correctly. We can see that if gamma naught, the capture ratio, is larger than 1, that is larger than 0 dB, there can only be one successful terminal transmitting its packets, and that is the terminal that has the strongest received power at the receiving site. We can think of systems with negative gamma naught as well. These could be spread spectrum systems where several packets could be correctly received as well. So let's review our analysis of the ALOHA system for the infinite user case and see how we can modify it for the case that there is a single transmission that can be lost, and for the other event where several colliding transmissions may still result in that one packet is correctly captured. So what we need to do is to recompute the success probability Q. And the success probability Q will consist of 2 components. One, that there's a single transmission, or there are no other transmission than I want a transmission, and at the same time there has to be no channel errors, so the packet has to be correctly received. And the other component is when we have a collision, and there may be K collisions, and there may be K minus 1 other transmissions. And then the success occurs if we have a capture, given that there are K different transmissions. And if we plug in our values, we can see that the probability that there is no other transmission is e to the minus gamma according to our exponential model, and 1 minus Pe is the probability that we have no packet error in a single transmission. And then we have the Poisson probability of having K minus 1 other transmissions in a slot times the probability that we have a correct capture of one packet given that there are K packets colliding. In general, it's quite difficult to compute the capture probability for a collision of K packets. But what we do here to start with is to look at a simplification. We look at the light load approximation, and the light load approximation is that we disregard from collisions of order 3 or more. So if there's a collision, we assume that's only between two different stations. In this case, we will have success in the following way. We can simplify the condition for our signal to interference plus noise ratio. If there are only two stations involved, we could have success either if P1 is larger than P2 by a factor of gamma naught, or the reverse. In this case, we also neglected the noise, assuming that the received powers are high. And if we go to our equilibrium condition for the ALOHA system, we note that the number of packets per time unit that enter the system, lambda, has to be gamma times the probability of successful transmission. And the successful transmission will occur if there is no other transmission, or if there is exactly one other transmission, and then we will have a successful received packet with a probability PC. And as you note here, we have neglected all the other terms in the sum for collisions of higher multiplicity. So let's compute the capture probability in this simple case. Let's assume that we have a propagation conditions that are so that the received power follows a power law path loss, meaning that the received power at station I is some constant divided by the distance to the base station Ri to the power alpha. So then we can compute the capture probability as we have a symmetric situation depending on if P1 is larger than P2. The capture probability can be seen as two times the probability that P1 is over P2 is larger than gamma naught. And then we can plug in the our power law path loss and get the relation between the station positions, or the distances of the stations from the base station, R1 and R2. And expanding this expression, we get an integral. If we then condition on R2, cap R2, the random variable is equal to R2, and then we can multiply with the density function of the distance R2, and then we can decondition on R2. And even further simplified, we get this expression plugging in that small r2 is equal to capital R2. Then we need to plug in the density function of a uniformly distributed terminal, and if the stations are uniformly distributed over a circular disk with radius r max, we get the following expression where we have the expression 2r2 over r max squared. That's the density function of a uniformly distributed random variable over a disk of radius r max. And doing the math here, we can compute the capture probability as the expression we see on the right. Plotting the expression in the previous slides in a graph, we get the following offered load through throughput characteristics for some different capture ratios gamma naught. And as we can see, as gamma naught becomes very high, then we hardly get any capture, and the curve will be very similar to the standard ALOHA. But as gamma naught decreases, the capture probability will increase, and the throughput gets higher and higher. So we can see that the performance of an ALOHA scheme when we take the capture into account is very good if our system has a low gamma naught. It means that it has a very high resistance to interference. So it can withstand lots of interference and still have a good chance of having a correctly received packet. So this brings us to our first quiz in a cellular ALOHA system where the receipt power can be assumed to follow a power law with alpha to the 4. You're asked to determine the capture probability for a collision with 2 packets for the different capture ratios 5, 10 and 15 dB. And as usual, you pause the recording at this point and you do the calculations, and when you're done, you restart the recording and check out the correct answer. And here are the correct answers. You can see that you can simplify the expression plugging in alpha equal to 4 gives us the capture probability as 1 over the square root of gamma naught, and then plugging in 5, 10 and 15 dB we get capture probabilities of 0.56, 0.32 and 0.18. So for 5 dB you can see that the capture probability is quite significant. So what are the potential problems with the light load approximation? Well, as the name indicates, it's a light load approximation, which means that in this region here, when the offered traffic is high, the number of colliding packets will definitely be larger than 2 in generally. So our approximation doesn't really hold. So there will be multiple collisions at high load. And another important issue is that the transmitting terminals are no longer uniformly distributed in this case. It is much more likely that a transmitter close to the center of the cell or close to the base station will be successful than a station close to the boundary that is most likely to lose a collision. To look a little bit more in detail in what happens with the traffic distribution, we now look at the paper by Goodman and Saleh. And Goodman and Saleh looks as a model where we look at the particular user in question located at distance r from the receiver. And for the purpose of the calculation, we make a variable transformation so that u will be r to the power n, which is equivalent to the parameter alpha that we have used before. So this is an alpha power law. And with this variable transformation, we can see that if the ratio between ur2 and u of r1 is larger than beta, beta is our capture ratio here, then we have a successful transmission. So in the example we can see that if we have a user in question at ur, that transmission will be successful if the other potential transmitters are outside the annulus with the radius bur. We can look at the packet arrival in a small region, circular annular region around u, and we assume that that is sigma du, which is the arriving packets. And we can look also in the same way, look at the offer traffic that will emanate from a circular annular region of thickness du. We call that gamma u du, which is sort of the differential offer traffic load. And then we can compute the throughput. The throughput for the whole system will simply be S sigma times U max, and we can compute the total offer traffic that we have to sum or integrate over all the U's. We have to integrate gamma U over all the U's, and that will be the offer traffic per slots in the whole system. We can use our balance equation we used before. The input traffic has to be equal to the offer traffic times the probability of success, and we will have success if there is no other transmission in the vulnerable region. And this integral equation we can formulate here as a nonlinear differential equation with the boundary value that gamma 0 should be sigma. And we can now find a solution numerically to this differential equation, and the solution looks in the following way. As expected, the offered traffic here shown as a function of u, and you can see for u equal to 0 at the very center of the cell, all transmission will be successful. The station that is exactly at the base station will always win in all collisions. So that's why the offered traffic is exactly equal to the input traffic in that case. So Q, or our success probability, is equal to 1. And then the offered traffic will increase as more and more retransmissions are needed to get the transmission through. And at some critical point, Umax divided by beta corresponds to the case where stations are so close to the boundary that they can never have a successful transmission. If they collide with some other station, it will not be further away such that it can have a signal that is stronger by factors beta stronger than the original transmission. And plotting the throughput relationship, this is the same curves as previously, but turned over 90 degrees for different capture ratios. We can see the ALOHA characteristics, but we can also note that the curves are much flatter for low capture ratios. Let's also look at the pairwise collision model and see if it's accurate. What Namislo did in his paper is that he compared the probability of success if I packets collided, and he used the uniform distribution over a circular disk, and he can see the dependence on the propagation constant alpha. So the upper curve A is the fourth power that we've used before, and it's quite interesting to see that regardless of the number of packets colliding, the success probability approaches almost a constant value, which is slightly less than 0.5. An interesting question in radio communication systems is whether the signal variations due to fading actually affect the system performance, and how it affects the system performance. And this is studied in the paper by Arnbach and Blitterswijk. The authors realized that fading and signal variations, they cause packet losses. So even if we have a single transmission, due to fading, or the signal may approach the noise threshold, and the noise will cause the packet to be corrupted and lost. But at the same time, signal variations also increase the differences in received power between different stations, which means that the probability of capture increases. So the interesting question is which of the phenomenon is actually dominating. And in the paper by Arnbach and Blitterswijk, they found in most situations the second phenomenon dominates. So the performance of the systems actually increased by fading, as long as the average power is, of course, is high enough. And the curves we see here showing the throughput relationship, throughput offer traffic relationship, show very flat curves for high offer traffic loads when the capture ratios are low. corresponding to a very stabilizing effect on the ALOHA scheme. The probability of being in the high equilibrium in the ALOHA system becomes very, very low. So this brings us to quiz number 2. There are a couple of statements here, A to D, and your task is to find out which of the statements are true and which are false. And as usual, you pause the recording at this point and figure out the correct answer. And when you're done, restart the recording and look at the correct answers. So here are the correct answers. The capture phenomenon will mainly benefit terminals close to the base station and not close to the border. So the answer A is wrong. We go to B. Fading may cause packet losses also when there's no collision. Yes, it can. C. The light loss approximation assumes that at most 3 packets collide. No, that's wrong. Our approximation assumes that at most 2 packets collide. And finally, as more and more packets collide, the capture probability remains relatively constant. Yes, that is true according to the Namislo paper. And this brings us to the summary of the seminar. In fading channels, packets may be lost also when there is no collision, or a packet may be correctly received even if it's colliding with other transmitting packets if the signal differences are large enough. And the power capture benefits, of course, mainly stations near the base station, the spatial distribution of backlog station is not uniform, as stations closer to the cell boundary are more likely to be losers and will have to keep on retransmitting their packets. But it's also obvious that stations also close to the border will benefit from the capture phenomenon, as the competitors closer to the base station will have their packets successfully transmitted and will leave the systems and leaving room for the stations closer to the boundary. And we've seen that fading can actually be beneficial to the system as it increases power variations and increases the power capture probability. This is, of course, as long as the average signal to noise ratio is high enough.